This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All the goods in the world are going to have downward sloping demand, but the ones that we work on in this subject are going to be downward sloping, or at least the flat.
Okay, the flat?
Flat as in flat. Downward sloping, outward sloping, flat.
So we can say that the goods are always downward.
No, I'm not saying that. When you ask to solve problems,
Yes.
we will tell you the demand curve.
Yes.
And the ones that we do in this subject are going to be downward sloping.
Oh, okay. Another question is wait. When we talk about the supply and demand, right? When we said if we said do we have opportunity cost that will affect the demand curve, or you only affect supply curve?
What has opportunity cost got to do with demand and supply?
When we buy things on the internet, it saves our time. So the opportunity cost is lower for customers, for buyers.
So, sorry.
Lecture now.
Okay, let's walk and talk.
Alright guys, I think we should start. There's quite a bit of material to cover today, so please bear with me. Right? So we're at lecture 8 now. And just a quick recap on the lecture on Monday. So we had this flow where we had a uniform flow and a source, right? And we found the stream function for this flow. We found the velocities u and v. We know the stagnation points for this flow, and we also know the equation of the separatrix. Okay, and what we can do is we can then replace any streamline with a solid boundary. And what we did is we replaced our separatrix here with a solid boundary. Okay, and we got this flow over a half Rankine body. Right, so one thing which is important, or one of the objectives of this course, is we want to find out what are the forces acting on a solid body. So we want to know what's the pressure distribution around this half Rankine body. So the question was, can we apply Bernoulli's equation? And the answer is yes, we can apply Bernoulli's equation. And starting from the conservation of momentum equations in x and y directions, right? We are able to derive the Bernoulli's equation for an irrotational flow. Okay, and the Bernoulli's equation is valid throughout our whole domain. Okay. So if I have some point upstream of the flow, I've called it U infinity and P infinity, right? Free stream pressure and velocity. And I want to know what is the pressure and velocity on the surface of the half Rankine body. I can then very easily use my Bernoulli's equation. Okay? And these points do not have to be along a streamline. Right, so I could then derive, or I could then express Cp, my pressure coefficient, in terms of velocities, u infinity, u and v, and then since I know what my stream function for this flow is, I could then express Cp in terms of my coordinates x and y, right? And also as a function of U infinity and Qs, which is the strength of the source. Right? And this is the pressure coefficient for the flow field, okay? For the whole flow. But, right. So I basically just substitute a few more variables, constants inside, okay? And we get Cp to be a function of x and y, right? This is for the whole flow, all right? But we're only interested in the pressure coefficient along the half Rankine body. So what I've done is I've just substituted the equation of my separatrix. Okay? And what we get then is our Cp just as a function of y. Okay? So I've plotted the pressure coefficient along the surface of the half Rankine body, and vectors which are pointing inside of the solid body means it's high pressure coefficient, and vectors which are pointing outward of the solid body is low or negative pressure coefficients, right? So you can see that here, when at the front of the half Rankine body, where the velocity is 0 at the stagnation point, you're going to have high pressure coefficient, okay? And when the velocities accelerate as it moves around the half Rankine body, you're going to have low pressure coefficients, right? Okay, so for a flow over a solid body, you're going to have forces acting normal to the surface, okay, due to the pressure forces, okay, and we're also going to have shear stress, right, which acts parallel to our solid body, surface of our solid body, okay. Are we considering shear stress for this course, for an inviscid flow? What did we do to our momentum equations when we derived the Euler's equation? We assume inviscid flow, right? Which means that the right-hand side terms, the shear stress terms, are all neglected, right? It's all 0. So we will be ignoring shear stress due to skin friction, okay? For this potential flow course, right? So we are only considering the normal stresses due to pressure, all right? So the net force acting on this airfoil, right, is F at some angle, and we can decompose this force into the force perpendicular to our free stream, which is the lift force, okay, and the drag force, which is parallel to my free stream, right? And I'm sure all of you know this already. Okay, so I'm going to consider the pressure force acting on an element of an airfoil, right? So I've just zoomed into a small part of the airfoil. Okay, and this small element has an area of dA, and some pressure is acting on this surface dA. So the force acting on this surface dFp, all right, is just equals to pressure times this small area here, dA. Okay, and this small force can be decomposed into lift, dL, right, equals to negative P dA sine theta. Okay, negative because it's in the opposite direction as dF. And dP, the drag, is going to be just P dA times cosine theta. Right? Anyone following so far? Yep. Okay, so I can then integrate this with respect to sorry, I can just integrate dl and dp for the whole surface area of the airfoil. Okay, and I should be able to get the whole or the net lift and drag acting on this airfoil. Okay, and I think this is something which you all will be doing in your airfoil lab. All right, so back to our half Rankine body. So we can replace our horizontal separatrix with also a solid boundary, right? So remember this horizontal line along the x-axis is also our separatrix, and I can replace it with a solid boundary, okay? And we can model, well, this flow is, I guess, kind of models a flow over a cliff, all right, or a flow over a front of a car, okay, depending how you see it. So if I have a photo of the Great Ocean Road, all right, it looks like we're modeling the flow over a cliff at Great Ocean Road. And along these streamlines here is one of your friend paragliding and parasailing, right? So we can also play around with our source. Okay, now if my source is not at the boundary, what must I do to ensure that my boundary is impermeable? Right? So I have to use the method of images, right? So if my source is not on the boundary itself, I would need to use the method of images to ensure that my boundary is impermeable. Okay, so look at the image which I have, below here. I don't know whether you can see it. Okay. Right, and just by altering the height of my source, okay, it looks like I can model a flow of a double body problem. So a flow over an inlet, right, where you have some kind of uniform flow, and flow is going into this inlet here. Okay, and this is our solid boundaries. Okay, so I've plotted the pressure coefficient on the surface of my half Rankine body, okay? And I just want to have a look at what happens to the pressure coefficient as my vehicle, right, or as I place this source closer and closer to my boundary, right? So have a look at the pressure coefficient. Okay, what's happening to the pressure coefficient at the bottom of this vehicle, or at the bottom of this half Rankine body? It's decreasing, right? Okay, sorry, this is no more half Rankine body, by the way. So this vehicle, you can see that there is very low pressure occurring at the bottom of this vehicle, right? And as I make it even closer to the wall, you can see that I have very, very low pressure at the bottom of the vehicle, and I have a net downward force acting on this vehicle, right? And that's why a lot of hypercars and F1 cars are very close to the ground, right? Because they want to, when the cars are very close to the ground, the flow accelerates underneath the car, all right? And it sucks the car and gives better traction, right? Okay, so we can also model more complicated shapes by adding, for instance, another source, okay, to this flow, right? And if I add a source there, you can see that this shape here looks something like a flow over a high-speed train, okay? And I can then calculate the forces acting at the front of this high-speed train. Okay, so there's a couple of problems with this uniform flow and a source flow. Okay, the first thing is that the body is infinite in the x direction, right? So this half Rankine body is infinite. Okay, and you can see that this here goes till negative infinity. Right, the other issue with this half Rankine body is that we cannot vary the angle of attack. Now, remember we want to, I guess, model a flow over an airfoil, right? And we want to also change the angle of attack of the airfoil, okay, to, I guess, analyze the lift and drag acting on the airfoil when you change the angle of attack. Right, but for this half Rankine body, you can see that your half Rankine body is always parallel to the flow, okay? And this means that you can't vary the angle of attack of this half Rankine body. Okay, so we have two issues, but let's settle the first issue first. So we have a source which caused the initial parting of the uniform flow, right, which is here. So now if I want to close this half Rankine body, what do you think I should add downstream? So a source parts the uniform flow. If I want to close my Rankine body, what should I add here? Some downstream location. A sink. Very good. Right. So I then just use a sink to close the streamlines. Okay. Right. So let's consider a flow just with a source and a sink. Okay. So I have a source on the right and a sink on the left, and they are located at plus minus s along the x-axis. Okay. Now you should be able to write down the stream function for this flow. Okay. And we can write them in cylindrical coordinates, right? So I'm going to have q over 2 pi alpha a, sorry, theta a minus q over 2 pi theta b. Okay, and theta a and theta b is just the angle at some location, all right, x and y. Right, so I can group q over 2 pi together, and I'll get my stream function to be q over 2 pi bracket theta a minus theta b. Okay, so we want to find out what the streamlines for this source and sink flow looks like, right? And we know that streamlines are lines of constant psi, okay, which means that q divided by 2 pi theta a minus theta b has to be equal to constant. Okay, so the angle, all right, or the difference between theta a and theta b has to be a constant. Okay, and hopefully you know, right, that when theta a minus theta b is a constant, that basically means that your streamlines has to be circular. Okay? Right, I'll show you again. Okay, so at all angles, okay, theta a minus theta b is a constant when your streamlines are circular. Okay, so let's try and prove this if you don't believe me. Okay. Okay, so I've just written my stream function, and I would like to write it in cylindrical polar coordinates because it's just a bit easier for this case. Okay, so I'm just going to get theta a minus theta b. Oops. That's pretty good. Okay, and we know that this has to be a constant for a streamline. Okay. Okay, so I'm just going to rearrange my equation. So I'm going to get theta A minus theta B to be equal to 2 pi psi over Q. Okay. Right, and my first trick is I want to take the tangent of theta A minus theta B. Okay, so I'm going to end up with tangent theta A minus theta B equals to tangent 2 pi psi over Q. Okay, and I'm just going to say that this is going to be equal to some constant A. Okay, and that's because you all know that this is a constant, right? Therefore, this is a constant, and I'm just going to call it constant A for now. Okay. Oh, oops, not yet. All right. I want to expand this term here. Do you all know how to expand that term there? Yes? No? Maybe? What theorem can you use to expand tangent theta A minus theta B? Right? Use the difference theorem. Okay, if you don't know what's the difference theorem, go back and Google it and YouTube it, all right? So I'm going to use the difference theorem. Okay, and basically what the difference theorem says is that I can express tangent theta A minus theta B as tangent theta A minus tangent theta B. Okay. Divide 1 plus tangent theta A tangent theta B. Right, seriously, if you guys don't know, please look it up, okay? Okay, and that's going to be equal to my constant A. And I'm going to call this equation 1. Okay, but what is tangent theta A and tangent theta B? What does it physically represent? Jump too much. 1? What? So you have to go back to the diagrams again, okay, to find out what tangent theta A and theta B are. What are 10? Okay, so luckily I have the diagram here. Okay, and I can express tangent theta A and theta B in terms of x, y, and s. Can you all see how to do that? Okay, so this is what have I done? So this is my x, right? This is my y. Sorry, this is my y, this is my x. Okay, so let's look at tangent theta A. So this is theta A. So tangent of theta A, what's that going to be? It's going to be y x minus s. Okay, very good. Okay. So this one here is y. Okay, so I hope you all can see that. Right, so I know that tangent theta A is just y over x minus s. Okay, and very quickly, what is tangent theta B going to be then? It's going to be y again, yep. Now it's going to be x plus s, right? Oops. Okay, so I know what tangent theta A and tangent theta B are. So I can just substitute that, these terms here, back into this equation here. Okay? Oops. Okay, so therefore, I'm going to get y over x minus s minus y over x plus s. Okay. And divide the whole thing. Oops. 1 plus y over x minus s, y over x plus s. Right, so I'm going to expand these terms here. I'm going to multiply that with that, and this here with that. So I'm going to get y x plus s minus y x minus s over x minus s x plus s okay, and I'm going to get in the denominator, I'm going to get x squared minus, x squared minus s squared plus y squared. Over x minus s, x plus s. Okay, and this term and this term here cancels out. Okay, and this one cancels out as well. Okay, so it simplifies to 2ys divided by x squared minus s squared plus y squared equals to our constant a. And all I'm doing is just I'm rearranging it. So I want to get this term here on the right hand side and a to be on the left. So I get x squared minus s squared plus y squared equals to 2sy over a. Okay, and I can actually take all the y terms together. So I'm going to get x squared plus y minus s over 2 squared equals to s squared 1 plus 1 over a squared. Okay, do you all know how I got this from here to here? Just completing the square, right? Okay. Now, can anybody tell me what this equation looks like? Does it look very familiar? Very good. So it's a circle, right? So if you didn't believe me before, I hope now you believe me, right? It's an equation of a circle. Okay? How should I do this? Okay. Okay, and the equation of a circle is x minus x naught, where x naught is just some shift, plus y minus y naught, where y naught is the vertical shift, equals to r squared, which is your radius of your circle. Okay, so hopefully you can see that your streamlines are circles with a shift of s over 2. So the center of your circle is located at s over 2, and it has a radius of square root this term here. Okay, so if I were to draw my streamlines, okay, my streamlines would be located at the center. That's not quite center. Let's try and... Okay, it will be located at the center here. Okay, and I know that height is going to be S over A. Oops, what have I done? Sorry, it should be S over A, not S over 2. Ah. Okay, this should be S over A. S over 2. Right, and your radius of this circle is going to be square root S squared plus, S squared bracket 1 plus 1 over A squared. Okay, and I'm just rewriting that equation there. All right, and S is basically just your spacing of your source and sink. Okay. Okay, everyone following so far? Yes, can I move on? Okay, so this is just for a source and a sink. Okay, the streamlines for a source and a sink. Now we're going to go back to our flow which we were looking at, right? Which was a source, a sink, and a uniform flow. Okay, so for this flow, right, we have a uniform flow which is moving from right to left, okay, negative U infinity, so it's from right to left. I have a source on the right hand side here, okay, and a sink at the left hand side. Okay, now as I add my uniform flow, all right, as I increase U infinity, okay, you can see we have a flow that looks like that. And indeed, now we have closed our streamlines, right? So we now don't have an infinitely long half-Rankine body. Okay, so let's try and sketch this flow. Okay, so all I've done is I've changed from our cylindrical coordinates to Cartesian coordinates. Okay. Okay, so the first step, you guys kind of saw the answers, but right, the first step is always to write down your stream function. Okay. In this case, we want to write it in Cartesian coordinates, because it's easier to find our velocities later. Okay, so negative U, so negative U infinity Y, that's our free stream or uniform flow, plus Q over 2 pi arctan y over x minus s minus arctan y over x plus s. Okay. Now I forgot to tell you that our source and our sink both have the same strength, all right? Q. All right. Both source and Sink has the same strength. Okay, and hopefully you know that this is our source, x minus s, right? And this is our sink, which is located at negative s, right? So it's x plus s. Okay, so once we find our stream function, we want to find our velocities, and that's the next step. Okay, and this is quite typical of a tutorial or an exam question. Oops. You know what step 3 is, but pretend you didn't see that. All right, so let's find our velocity u. Okay, and u is just going to be del psi over del y equals to negative u infinity plus q over 2 pi. Okay, and you should know how to differentiate arctangents by now. So you get x minus s over y squared plus x minus s squared. And for your sink, it's going to be negative x plus s over y squared plus x plus s squared. Okay, and similarly for your velocity v, it's, never forget, negative del psi del x. Okay, so I'll end up with q over 2 pi y over y squared plus x minus s squared minus y over y squared plus x plus s squared. Right? Now, the next step, the third step, is to find my stagnation points. Okay? So now you can see my velocities u and v, right? We have an expression for them, and we want to find the location when u and v are equals to 0. Now, hopefully you all can see quite easily for v is 0 when what 0? Right? When y 0, v 0, okay? And that's what we've got here. So y equals to 0 gives you v equals to 0. Okay? The next step is then to substitute y equals to 0 into my velocity u. So we want u to be equal to 0, to be equal to negative u infinity plus q over 2 pi. And it's just going to be 1 over x minus s minus 1 over x plus s. Right? Okay, and I hope you all know how I got that, because y is equals to 0, right? So this term and this term, is that right? Wait, hold on a second. Oh, yeah, so y equals to 0, right? So I can cancel out here one term, so I get 1 over x minus s, and I get to cancel this term here as well. So I get 1 over x plus s, right? And that's how I end up with this here. Okay, so all I do then is just rearrange this equation here. So hopefully you can see that I'm going to get x squared equals to qs over u infinity pi plus s squared. Sorry, there's no qs, it's just q. Okay, so I've just expanded this and then rearrange it to get this equation here. Okay, nothing fancy. Is it okay? Have I done anything silly? Which one? Oh, is there an S? It should be a QS, is it? Oh, right, sorry. I should have an S here. All right, yep. Okay, yep, that's correct. And I can then find what x is, okay? So x is just going to be square root plus minus qs over u infinity pi plus s squared. Okay, and I'm just going to take out s squared. I'm going to take that out. So I'm going to get plus minus s q over u infinity pi s plus 1. Okay, so therefore, I know my stagnation points are located at they're located at plus minus s square root 1 plus q over u infinity pi s, and y is just located at 0. Okay, everybody agree? Okay, good. Yep. So, I know my stagnation point. I want to find the equation of my separatrix. Okay, so that's going to be step number 4. Okay, and I hope you all know that to find the equation of a separatrix, all I have to do is just substitute my stagnation point back into my stream function. So my stream function psi is going to be equal to negative u infinity, right? Y is 0, right? So that's multiplied by 0 plus q over 2 pi arctangent of 0 over some denominator minus arctangent of 0 with some denominator. Okay, and you should know that my stream function then is, my stream function constant is going to be equal to 0. Okay, good. Okay, and now I substitute this constant back into my stream function equation. Okay, so therefore, 0, okay, is going to be equal to negative u infinity y plus q over 2 pi s per p4, right? Arctangent y, x minus s minus I ran out of space. Okay. All right, and I'm going to switch back into cylindrical coordinates now. Okay. Now in cylindrical coordinates, and I'm going to bring this term to the left-hand side. So I'm going to get u infinity y equals to q over 2 pi. Okay, and arctangent terms are just theta a minus theta b. Now actually I want to bring these terms on the left hand side as well. Okay, so I'm going to get 2 pi u infinity y over q to be equal to theta a minus theta b. Okay, and I'm going to do the same trick which I did before. Now I'm going to take the tangents. Oops. Okay, I want to take tangents for both sides. So I'm going to get tangent 2 pi u infinity y over q equals to tangent theta a minus theta b. Okay, and do you know how I can expand this? Do you know what this is? What this term is? Oops. It looks very similar, right? Didn't we do something similar before? Go back a few pages in the notes. Yep, so it's going to be, I can express it in terms of x and y, right? 2ys over x squared plus y squared minus s squared, right? Okay, and if you don't know how I got this, I'm just going to flip back to a source and sink. Okay. So remember, how we got this equation here? Wait, where is it? This one? Remember this? Okay. And that's just equals to tangent theta a minus theta b, right? Okay. So all I'm doing is I'm just substituting this into tangent theta a minus theta b. Okay? Everyone following? Yep. Good. Okay. All right. And we'll continue tomorrow. All right. Yeah. Right. Yeah. We'll look at this flow tomorrow. Yeah. Okay.